Hello, Physics 30s. It's Mr. Jukley here again. Today we are going to go through our Unit 6, Lesson 4. It's Mass Spectrometers. This is a wonderful, beautiful lesson because it really looks at the, I suppose, applications of what we can do with half-lives and the technology that we use to do those applications. It's all about mass spectrometers, so devices that figure out the mass of individual isotopes for us. And that might not sound very important right now, but this is a huge, huge, huge thing, especially in archaeology and trying to figure out how old stuff is, oddly enough. So yeah, and I guess the other really nice thing about this lesson, mass spectrometers, is pretty much all of it is stuff that you've learned before, just again looking at it in a new light. So there's no new math, there's no new big ideas, with the exception of this device, the mass spectrometer. So let's just jump right in. The mass spectrometer, again, is a device used to separate and identify the different isotopes of an element. So you may have seen things in CSI. I gotta lie, I'm not gonna lie, I've never actually seen an episode of CSI, but I've seen parts of one, and they use all kinds of cool technology that does not exist to solve crimes. They do, I believe, use mass spectrometers to figure out exactly what's going on. Real archaeologists, though, real archaeologists and forensic people can use mass spectrometers to figure out how old this particular tablet is. This one looked up, it's possibly the world's oldest to-do list. I don't know why you would do a to-do list in rock, but that's fine. If it's anything like my to-do list, it gets erased and rewritten all the time. So this is sort of a simplified view of our mass spectrometer. So we'll go through the different parts of this together, but things that we need to know about here. We need ion generation and acceleration chambers. So we've got some electrons that will blast our sample, which will ionize our sample, and then we've got this parallel plate apparatus, that will accelerate are now ions that are going across. Then we've got a magnetic field and an electric field. So I guess I'll underline the positive and negative plates so we know there's an electric field there. And essentially what's going to happen with that is it's going to be our velocity selection chamber. So it's going to make sure that everything that's passing through is going at the exact same velocity. And we'll talk about that in more detail in a little bit here. But you probably already starting to guess it's based on balanced forces. So the balanced magnetic and electric force. And let me just think about this for a second. So those are going to be positive ions. So I think the electric force is going to be downwards. That means the magnetic force has to be upwards. And we've dealt with that idea of balanced forces before. Then they're going to enter a secondary magnetic field, and they're going to go into circular motion. And they're going to curve at different rates. And then finally, we've got an ion detector and collector, where it's going to collect the relative amounts of those two different samples. So looking at this, like, have we dealt with ionization? Absolutely, we have kicking out a couple electrons, knowing what the charges are. Have we dealt with charged particles accelerating across parallel plates? Totally. Have we dealt with balanced forces, balanced in particular magnetic and electric forces? Most definitely we have. And then finally, have we dealt with charged particles moving in external magnetic fields? Going into circular motion? Oh yeah, you bet. So every section of this we've dealt with before. It's just putting it together in this one device that we're looking at today. So I showed you the simplified version. A real mass spectrometer is a little bit more complicated, but the basic ideas are the same. So the first step, ion generation. So I've got my electron hanging out in its ground state. I want to be able to kick it out. There's a whole bunch of different things that we could talk about for the math for this. We could talk about energy levels and how it needs the electrons coming from the electron beam need to have enough energy to kick those electrons out. So all kinds of different things talking about that. I think I want to talk about simple math with you here, though. Very, very simple math. Q is equal to NE. You remember that one? All the way back from Unit 2. So if you're thinking on this one, Q is the total charge in coulombs. N is the number of electrons lost or gained. In this case, lost because we're kicking out those electrons. And E is our elementary charge. So this is the math that tells us about the actual charge in coulombs of one of those ions. Now, some terms that we want to look at, they might be on the next page here. Yeah, there they are. Singly ionized, doubly ionized. So singly ionized is a term you could probably guess. Singly ionized means it's kicked out one electron. So when we're using Q is equal to Ne, it's essentially 1 times the elementary charge. Doubly ionized is still Q is equal to Ne, except now we are dealing with 2 electrons being kicked out. And we usually don't really put positives or negatives in these formulas. We usually think about that a little bit differently, but I put them in specifically here because if we're kicking out electrons, the charge of the ion will be positive. You get rid of some negative, you become more positive. Cool. There's triply ionized, there's stuff like that. Most of the time we deal with singly and doubly ionized. So that's the thing right there. Step 2 is we've got the ion acceleration. So I've chosen carbon for this one, or we've chosen carbon for this one. So thinking about carbon, and this one, if it's got a charge of 1 plus, again, we'd call that singly ionized. Well, that carbon's going to accelerate across these parallel plates. So you'll notice that we got the positive side over here, the negative, so that means this is all positive plate on this side. This is all negative plate on that side. And we know that, remember, the long side of our power source is positive, the short side of our power source is negative. And you'll remember that there were 2 physics principles, not physics principle 2, but 2 separate physics principles that we could use to deal with this. Do you remember what they are? If you're thinking physics principle 5 and you're thinking physics principle 1, good stuff, you're right on. So assuming that that carbon starts at rest, we're starting with some electric potential energy and we're going to finish with kinetic energy. Assuming that it goes across the entire potential difference or voltage, we know that electric potential energy is delta V times Q, and our kinetic energy is 0.5 mV squared. So we can absolutely 100% go through and solve for that final speed. We could figure out how fast it's going when all is said and done. Cool. And I would, I'd honestly recommend using this one for the most part. It's a little bit easier, something we've been doing since since physics 20, I suppose. Okay, the other one that we want to look at here is physics principle 1, which is all about acceleration. So when we're talking about net force is not equal to 0, we're going to say net force is equal to Fe, and net force, it's going to be equal to our electric field times our charge when I expand on that. And then I can also expand, I don't know why I didn't do these both at once, mass times acceleration is equal to electric field times the charge. So again, expanding them all out. We can think about this in terms of electric field. Well, that's just our potential difference divided by the distance across the plates. And there's sort of, well, it's one of our setbacks, is we're not always given the distance across the plates. And we need that in order to find our electric field. So we kind of need that for this one. The other setback that we see with physics principle 1 sometimes is once we solve for acceleration, we know VI is equal to 0. We're typically looking for VF. So I'm going to put that as our question mark. We can solve for acceleration. Again, we need at least one other thing, so either time or distance, and a lot of times we just don't know. There's too many unknowns to use physics principle 1. So I like to stick with physics principle 5 for the most part when I can. Cool. 2 big ideas with this. The third step, I don't know why I'm stuck on step 2, but our third step is velocity selection. So we want all of these atoms to be going the same speed through. So once they're accelerated, they're going to start at different places. They're going to have different charges. They're going to be going all kinds of crazy different things. We want them to be going all exactly the same speed by the time they get into that secondary magnetic field. So different speeds to start, we want them to be same speed to end up with. So what we do with this is we essentially use balanced forces. So I can go through and I can kind of think about this here. I've got my positive plate on the top, And we know that these are, I believe I was using carbon before, so we know that these are positive carbon ions. So I've got a positive plate up top, negative plate on the bottom. We know that we've got our electric force going downwards. If it needs to be balanced forces, that means I need an equal but opposite force going upwards, and you're probably already thinking to yourself, oh yeah, equal to opposite forces, that sounds like physics principle 0 to me. Perfect. So one thing that I want you to think about here, I'm going to have to put the video on pause and get out my hand rules. Could we figure out the direction of the magnetic field here? I mean, honestly, could we figure out the direction of the electric field as well? Electric field might be a little bit easier. How do we know the direction of the electric field? It's the direction a positive would want to go. So I know my electric field is downwards. Magnetic field a little bit trickier. I'm going to put it on pause. I'm going to go find the appropriate hand rule. Not like, on my left or right hand, but in the pictures of hand rules that I have. I'll be back in a second. Okay, awesome. So I picked out my right hand rule number 3. Whoops. Right hand rule number 3. I remember that my thumb is the velocity of the charged particle. My pointed fingers, and I always use the flat palm version, but my fingers, there we go, are the direction of the magnetic field. And then finally, my palm is my magnetic force. Of course, if you're using the other version that's like the physics gang symbol style one, your thumb is still the velocity, your pointer finger is the magnetic field, and your middle finger is the magnetic force. But should still work out to be the same either way. So we know that the velocity is towards the right. We know that the magnetic force is upward, so I need to have those two things align. Okay, so magnetic force, that means my palm has to be upwards, and my thumb has to be towards the right. The only way that I can line up my hand is if that magnetic field is into the page, right? So my fingers are pointed into the page. Nice, okay, so we've talked about that one a little bit more too. Let's get rid of that hand rule over there. Back to my felt pen. There we go. So physics principle 0, let's see. So we've got, no, I already wrote physics principle 0, so let's try again. We've got our F net is equal to 0, which means that our magnetic force must be equal but opposite to our electric force. And I'm going to leave out the negative for the opposite sign. We'll only deal with magnitudes here. So Fm on a charged particle, well, that's QV B, and our electric force is our electric field times charge. Cool, cool. See anything that we don't even need? That's right, charge at this point. Who cares if it's singly ionized or doubly ionized? Right, charge is going to cancel out. So then my speed is going to be, let's see here, it's going to be my electric field divided by my magnetic field. Awesome. And then also just note that our electric field, remember, is delta V divided by delta D. I'll even write that out again. Electric field is equal to delta V over delta D. And also, it's been a while since unit 2, I suppose. Please don't confuse electric field with electric potential energy. One's got a little arrow over top because it's a vector, the other not so much. Cool, okay. So, things to note here with this one, like we say that this is a velocity selector. What happens if it's traveling too fast though? Like that's one thing to think about. So does my electric field, is that affected by speed whatsoever? Not so much. What about my magnetic, sorry, I said field. My electric force, is that affected by speed? No. What about magnetic force? Yeah, it's got speed in it right there. What's the relationship between magnetic force and speed? It's a direct relationship. So if it's going too fast, its speed is too large, it's going to have a larger magnetic force, but the electric force is still going to be exactly the same, right? So larger magnetic force, but electric force is going to be the same. Let's see, magnetic force is there. It's going to cause it to curl up and smash into the this plate over here. Not actually going to make it through the velocity selector. Any guesses as to what's going to happen if it's going too slow? Again, the magnetic force has a direct relationship with the speed. So if it's going too slow, the magnetic force is now going to be too small, or at least smaller than our electric force. So it's going to cause it to curve down and smash into the plates. It's not going to pass undeflected through that little hole. Cool. Okay, the very, very last step is ion generation. So now we've got these ions, they're entering this external magnetic field. Could we figure out which direction that external magnetic field is? I need to get my hand rules out again, so I'm going to put it on pause. You think, you probably already guess, it's right hand rule number 3. Rule number 3. So the velocity is going this way. It looks like my magnetic force initially is going down because it's causing them to deflect downwards initially and enter circular motion. So yeah, I got to put it on pause for a second here, but I'm going to get out my hand rules. Alrighty, so I got right hand rule number 3. My thumb, let's see, that's the velocity, has to be towards the right. So it's got to be that way. The magnetic force needs to be downwards. My palm needs to be downwards initially. So the direction of the magnetic field for this particular one must be coming out of the page. Excellent. Excellent. It almost looks like a person in distress, the thing that I've got drawn right there. Looking sad, maybe throwing up particles or something like that. Put an eyebrow on it. Right. Okay, I'll stop that. Anyways. Let's put that off to the side, stay in the corner. Okay, and let's get back to this. So you might be thinking to yourself, okay, circular motion, what physics principle is circular motion? Oh yeah, that's right, physics principle 2. So we've got the same sort of ideas. Remember, physics principle 2, F net is the sum of all forces, and F net is mass times acceleration, except we're dealing with special F net, which we call FC for centripetal force, and AC for centripetal acceleration. So in this particular case, we've got FC, well, what's causing it to go in a circle? FM. So I'm going to expand on this a little bit. This is M times AC. Very nice. FM is QVB. Excellent, excellent, excellent. Okay, and then let's expand one more time. Usually we're dealing with speed, so AC is V squared divided by R. There we go, V squared divided by R, which is going to be equal to QVB. Excellent. Anything cancel? Oh yeah, it looks like one of the speeds cancels. Nice. So we get M V over R is equal to QB. Now the really important thing from this as we go through and as we're checking this out is, well, we know the difference from the radius, right? When I look at this picture over here, I can clearly see that I've got in this case, two different isotopes. Isotopes have different masses. So what we want to look at for this is the relationship between mass and radius, right? Relationship between mass and radius. And even what we could do is, I'm just going to solve for mass, to be honest with you. Q, B, R over V. We could even figure out the masses of those individual isotopes if we knew their charges, we knew the magnetic field, we can measure the radius, and we can figure out the speed in the velocities section. So let's go through and let's have a look. Just one last little relationship here. Mass has a direct relationship to radius, or you could say it the other way, radius has a direct relationship with mass. So when I'm looking at these two things, I'm going to label them here for us. I'm going to label them ion 1 and ion 2. Which one has a bigger mass? Ion 1 or ion 2? Well, ion 2 has a bigger radius. Bigger radius means bigger mass. So this one is bigger in terms of its mass. This one must be smaller mass. Cool. All right. So we've separated them based on mass. We still haven't seen how this relates to half-life, have we? No. Still haven't seen how it relates to half-life. Still haven't seen really what this is for at all, other than separating different isotopes. But anyways, let's check it out. That's the next part to get into. So if we're dealing with carbon, two very common isotopes. Well, I guess one is very common and one's less common, but carbon-12, very, very common all over the place. Most carbon is carbon-12, but we've also got this kind of oddball carbon-14, so a couple extra neutrons added in that. Carbon-14, the bigger one, again, would have the larger radius. We could do this for all kinds of different things, right? So if we took a sample of, I believe this one is mercury, so if we took a sample of mercury, we could break that that mercury apart into its components, into each individual mass of its elements, and we'd see, okay, there's not very much in a natural sample, so this is just a big chunk of mercury that's been vaporized. There's not very much 196, a little bit of these ones in this sort of area. Doesn't like to show up naturally as this one. This one, pretty popular there, mercury 202. Quite a bit of that shows up in our natural sample. So when we break this apart and when we separate it based on their masses, we can now get an idea of what the average atomic mass of mercury is. Where's my periodic table here? Let's just check it out. 200.59 is our average, and that's what we see on our periodic table, AVE or AVG. I don't know, I always write AVE, but so 200.59 would be the average of all of those isotopes, those naturally occurring isotopes. So pretty cool. That's where all those random numbers come from on our periodic table. We also get an idea of the relative amounts of which ones, and we talked about with the darkness of the line on this one, if we were to graph it, we could figure out the relative amounts of each isotope, which is kind of cool. Okay. We can also do carbon dating with this. This is a cartoon that doesn't actually make sense. So little kid says, don't worry, Grandpa, if you can't remember your age, we'll get you carbon dated, which doesn't actually make a ton of sense because carbon dating doesn't work for living organisms. So separating those isotopes, and this is where the half-life starts to come in, it helps us determine the age of a particular material. So carbon-14 is what we're going to start with. Carbon-14 is used for a lot of previously living things, so like archaeological sites in the last like 60, 70,000 years, bones in the last 60, 70,000 years, stuff like that. So anyways, essentially what happens with this is it all starts off with cosmic rays. Cosmic rays come down, they pass through our atmosphere, they create fast-moving neutrons. All right, no problem. Those fast-moving neutrons, they interact with our atmosphere, and they in particular act with nitrogen 15 in our atmosphere, so an isotope of nitrogen. And you know what? I had to put it on pause there and think about something. This is a bit of a mistake on this one. Anybody spot the mistake? First off, nitrogen 15, very, very, very uncommon. Very uncommon. Nitrogen 14 is what we're really looking for. And then our physics principle, do you remember the physics principles that correspond to these nuclear reactions? It's physics principle 8 and physics principle 7. Physics principle 8 doesn't actually work out for the way this is written. So let's see, I've got on this side 16 nucleons in total, and on this side only 14. Something funky is going on there. Absolutely funky. And I'll tell you what it is right now. This is actually nitrogen 14. So my bad, but good on you if you figured that one out. Now physics principle 8 for our top numbers, our mass numbers, makes a lot more sense. And physics principle, let's see, 7, conservation of charge for our bottom numbers, our nuclear charge. Well, it made sense before. Okay, perfect. So here is the nuclear reaction. This is not a decay reaction, and there's tons of different nuclear reactions that can happen. Not one of our 3 decay reactions, but we've got that fast-moving neutron collides with nitrogen-14, remembering that like 70% of our atmosphere is nitrogen-14. As it collides with it, it kicks out a hydrogen, and it also creates our carbon-14. So there's a big part of our carbon dating. Now that carbon-14, well, it does pretty much everything that carbon-12 does. So it reacts with oxygen and in our atmosphere makes carbon dioxide. Pretty straightforward. We've seen that before. So our carbon-14 and our carbon dioxide, well, we know that plants, they like carbon dioxide. They eat up that carbon dioxide. They take it out of our atmosphere. They turn to sugars, and then we use sugars. Thank you, plants. Next time you see a tree, high five a tree. We wouldn't be here if it wasn't for those plants and those trees. But yeah, they take it up, they create sugars, they do their thing, and then within that plant, within that tree, the percentage of carbon-14 stays as a fixed amount, stays very, 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 very constant for living things, and it's about 1 trillion regular carbons for every 1 carbon-14, approximately 1 trillion for every one. Or you could think about this as 1.3 times 10 to the negative 12 carbon-14s for every 1 regular carbon. So either way means essentially the same thing. Now, when we think about this, like that tree, as it's living, it's got the same amount of carbon in it. 1 trillion to 1 is the ratio. Let's say a bear, I don't know, a deer, we'll say, eats part of that tree or some of the grass, or a cow eats some of the grass. The cow now has that 1 trillion to 1 ratio, and that's a fairly common ratio, right? 1,000 or 1 trillion to 1 for pretty much all living things. But as soon as it dies, right? As soon as that tree dies, it is no longer taking in carbon dioxide. So no longer taking in carbon dioxide. So that means we are fixed right at it with its right at the moment of its death with 1 trillion to 1. Cool. But carbon-14 is a radioactive element, which means it likes to break down. It likes to go through decays and turn into something else. We'll talk about what it turns into in a moment here, but it likes to turn it down everything else. It's got a half-life of 5,730 years, which means after 0 years have passed, that percentage or that ratio is, the percentage is 1.3 times 10 to the negative 10% carbon-14, or again, about 1 trillion regular carbons for every 1 carbon-14, carbon-12s to carbon-14s. After 5,370 years, we'd have half as much. After 11,460 years, we'd have a quarter as much. You can kind of see where this is going. So if we can measure the difference in percentage between carbon-14 and carbon-12, could we figure out the age of something? Absolutely, absolutely we could. So by looking at that percentage, we can figure out how old stuff is. Issue is, carbon dating doesn't really work very well for anything more than about 60-ish thousand years old. Any guesses why? So percent parent, actually in this case it wouldn't even be percent parent. What does our graph look like? Yeah, I guess it is sort of percent parent for this one. Versus time. Well, after 1 half-life, starting with 100%, I'd have half as much. After 2 half-lives, a quarter as much. 3 half-lives, 4 half-lives, 5 half-lives, and so on and so on. 6 half-lives. Do we ever actually reach 0? This is one of those graphs that kind of comes down like this. In math, you learn about asymptotes. But in physics, is it really an asymptote? When you get down to that very, very, very last atom, that last atom decays, there's nothing left. Even before that, typically, there's just so little that we can't detect it. So we eventually run out of carbon-14, and then we can't figure out things more than 60,000 years old. If we want to figure out older things, we need to use things with longer half-lives. For example, the age of the Earth, using uranium and lead. So uranium-235 and uranium-238 to figure that out. There's a fantastic episode of Cosmos on this. It's about a guy named Claire Patterson, who is like a real-world superhero. He actually saved millions of people, billions of people on the world, and also at the same time discovered the age of the Earth. I forget which episode it is, but it's definitely worth a watch if you got access to those. Cool. Okay, so I think that's about it for today. So good stuff. Oh, I should draw the other one. Oh, that looks worse. I'm not. Okay, yeah, we're done. We're done. Have a great day. Check out the practice from this. Remember to practice until you're really comfortable with it, until you really think you understand the ideas. I know there's no actual examples for this one, but the good news was it was all review, right? Just a new tool with all of those old concepts. Anyways, good talking to you, Physics 30s. Talk to you again soon. Bye for now.